this Friday.
And I've shifted those due dates for both homework 1 and 2 to be due this Friday. You should be able to complete both of them on Friday. We'll see how far we get in lecture today, and I might double back. So after class at some point today, I'll go back through the homework questions and decide if I think they're all fair game or not. Okay? For those of you that started the online IR lecture, which is based technically on chapter 13 if you're counting, there's a homework number 3 assigned for that. One of the issues, as I was actually recording the lecture, I realized that there's some terminology that pops up within that section, i.e. hybridization theory, that we hadn't really gone over. So if anybody took a jump start and tried to get involved with that IR material, you're going to, what's this SP2, SP3, how do I find that, how does that apply? Okay, how do I build these structures? Until we talk about how we build those structures, which we'll get to today, that homework's going to become a little bit more difficult. So I pushed that deadline back to all the way to Sunday so you don't have everything crammed at the same time. You should be able to complete homework number 3 by Sunday based on the material from today. Okay? When it comes to IR, it's very easy to overanalyze it. Okay? If you've ever seen little kids play with those boxes where you put the little shape through the shape hole, okay, into the box, that's a vast oversimplification of IR, but that's kind of the level that you should be thinking about when it comes to IR. Match the shape, put the shape in the hole, that means it's a star. Okay? The shape looks like an OH, that means it's an OH. Okay? Treat it in that respect. One of the other big problems that you'll encounter is that some of the problems don't give you structures but list names of compounds. You are not expected to know names yet. Okay? Probably the least, or my least favorite section of organic chemistry has to do with names, because I just think it's kind of boring. You have to follow somebody's old guy's rule to come up with the name. What I expect you to be able to do now is to go through and look up those structures. The online homework is online, which means to access it, you are necessarily online. Use Google. Enter in the name of the compound into Google and get a structure. Look at that structure and use that to match back to the IR spectrums. Okay? So take advantage of that assistance. I do not expect you to sit down with any homework assignment and do it on your own with no outside help. Okay? No teacher expects that out of the homework. You are expected to go back to notes, lectures, textbook, online resources, do whatever you can to help get that information in there. Chapter 3, homework number 4, was originally set, I think, to be due this Friday as well. We're not even going to get into chapter 3 until at best, probably Monday of next week, maybe Wednesday. Okay? I would expect that you might remember some of that and be able to answer those questions, but we haven't talked about it yet, so I've definitely pushed that deadline back, or that due date back. Okay? You can fully expect to have at least 1 homework due per week. Ideally, we're going to get up to 2 homeworks per week, and probably will fall in that 10 to 15 question range. Okay? Questions about any of that? Does anybody feel a little bit better, maybe a little bit less stressed? Okay, a little bit? Okay, that's good. After exam 1, it'll get a lot worse, trust me. You did have a question?
Yeah, about the lab. Is that just the homework?
So,
or is that a separate
no, the lab is a separate assignment. So when you look at the lab, the lecture is the same for both of those. The lecture portion of the course has the online sapling homework as problems to work. The lab portion of the course has an online IR assignment that you would print off and complete. Okay. That one's a little bit more straightforward and something that I would directly expect you to be able to do because the structures are given to you. You don't have to go look them up. There's the structure, there's the spectrum, and play a matching game. Okay. So that one's a lot more on the par of what I would fully expect you to be able to do. Okay. And with the lab, we'll talk about that in lab 2. So if you still got questions on that day of lab, then we'll spend a little bit of time looking at it. Okay. Any other questions? All right, my nose itches. So we looked at Lewis structures and kind of the basic examples of how we can put them together, and we looked at some kind of more complicated examples. Okay? The intent behind this kind of section within Chapter 1 is to have you work a whole bunch of drawing out these structures, and that's because Formulas ultimately become pretty useless in organic chemistry. One formula could result in as many as probably 5 or 6 compounds, at least on the small formula scale. If we make those formulas even bigger, we could end up with hundreds of thousands of structures. If we change the structure, we inherently change all of the properties associated with that compound, and that defeats the purpose. Okay? So we want to really get towards being able to draw structures. Okay? One of the big things that falls out of Lewis structures that becomes really relevant for organic chemistry is this concept of resonance. Okay? So we're going to keep coming back to that, and that's going to be our favorite four-letter word. And I know that's not 4 letters, but it's close enough. Okay? So practice these. Start getting and looking for those resonance structures, trying to piece them together to get those figured out. It will help you in the long run. Okay? Instead of doing the Lewis examples there, I want to jump to our resonance page, and we'll do another Lewis example. Carbonate. Did we do carbonate last week? I think we did. Yeah. Okay. So we'll take a look at the cyclopropenyl cation. Okay. Again, it's not one I expect you to know the structure for, but if I give you some more information here. Prop stands for 3, so we've got 3 carbons. Cyclo stands for cyclic, so we make this as cyclic as we can. Okay. The ene here in the propenyl means that we have a double bond. So we put 2 bonds between our carbons. Okay. And then it says a cation. What is a cation? Positive charge. We would then also go through and put a positive charge, the most likely atom. In this case, it's going to be that one. One of the things that you'll find when drawing Lewis structures is that there's particular bonding patterns. When we take a look at carbon, how many bonds should an individual carbon atom have? 4. Do these carbons all have 4 bonds? No. So what do we have to do? One of the things that we end up doing in organic chemistry is implying hydrogens. We won't get to that yet, so let's go ahead and draw in those missing hydrogens. Okay, so those 2 carbons now have our 4 bonds. We can move up to our cation. I'll only end up adding 1 hydrogen. Why only 1 hydrogen? Okay, because it's charged. That positive charge means we got rid of 2 electrons. If we got rid of those 2 electrons, carbon can't make that 4th bond. Okay? So that ends up being our cyclopropenyl cation. Okay? If we'd gone through and done this in a Lewis structure fashion, what we would probably have found is ended up with a structure along these lines. An electron there and an electron there. Okay? And we could put them together to make that double bond. But are there other places we could have put that electron? Well, it turns out yes, and I'm going to go through some abbreviations now. What we could have done is instead of putting those electrons on the bottom part of the triangle, we could have put them on the side. Okay, what happened to do that? Well, what we're going to do is take that pair of electrons and we're going to move them over here. Okay. Notice the arrow I used has 2 heads to it. Why does it have 2 heads? How many electrons are moved? 2. 2 heads, 1 head per electron. So we're using a curved arrow to represent the flow of those electrons. We've now positioned those electrons in the upper right-hand corner. If we take a look at our top carbon, which I'll now go ahead and let's pick orange. What happened to that carbon? We draw it in on our red structure. Okay, so what we want to do, and we had 2 discussions on that. We could say lost the positive charge, and somebody else said gained an electron. When we look at organic chemistry, what do we move? Electrons. So when you discuss what's happening through a structure, you never look at the positive charge. You need to look at the electrons. That carbon started positive, but in the course of moving those electrons, what did it gain? It gained an electron. What charge is an electron? Negative. +1, -1? Neutral. That carbon is now neutral. So it's no longer charged. What happened to, I'll call it my green carbon. It started neutral, but in the course of this electron motion, what happened? It lost an electron. So if we lose something that's negative, we're doing minus a minus 1, and we have a positive charge. What we've done is moved those electrons through our structure. Right? We could go back through and draw on our hydrogens. Right? And as we move through the semester, we're going to stop doing that. But as we talked about it, we can go ahead and throw them in there. All right? What's the relationship between these two structures? We have the same atom connectivity. The only thing that's changed is where we put that double bond. Well, it turns out those double bonds were allowed to move. Okay? That double bond can shift in different places as long as we don't change the rest of the atom connectivity or the other atom connectivity. So what we're allowed to move is that double bond, okay, which we'll refer to later as our pi electrons. Okay? Is there another way we could have moved those electrons?
To the left side?
Yeah. We could have taken those electrons and we could have shifted them between those two carbons. Net result, put the positive charge on that other carbon. Which of these structures is the correct structure for the cyclopropenyl cation?
All three.
All three of them. So if you were asked to draw the Lewis structure, you would have to provide all three. What we're looking at is a mix of all three of these contributing to the overall structure. All right? Slightly different from the example we looked at last week, because I think we also had CO2, right? And if you were asked to draw the Lewis structure of CO2, this would be the answer you would provide, right? The other structure we drew up was this guy. Why is this structure not typically drawn as a structure for CO2? It's charged. The energy is inherently different from that other structure. If our energy is different, we always draw the most representative, the lowest energy structure. When we look at the cyclopropenyl cation, what's the difference in energy? They're all the same, which means we have to draw them all. Okay? So that's kind of what's going on with our resonance. We're looking at moving electrons throughout a structure without changing the basic backbone of the structure. We maintain the same atom alignment. Questions about that?
How would you draw the arrows for that one, for going for the CO2?
I'll show you that after class. You'll end up seeing that reacting in second semester, so we won't worry about it right now. So what electrons were we allowed to move? It was the electrons in the double bond, also known as our pi electrons. What electrons could we not move? Sigma, or since we haven't officially addressed that, our single bonds. The single bonds we're not allowed to touch. We can only move the extra electrons on top of it. Okay? So best Lewis versus useful Lewis. Okay, and this was one of the things that we were talking about, and actually I've got the opportunity to do it, so we can look at our CO2. 2 birds, 1 stone and all.
So best Lewis is
The lowest energy representation for the atom connectivities. You asked for what arrows we would use to go from CO2 that we would typically draw and that goofy looking CO2 that I drew later. What changed? What bond? One of the double bonds moved where? To the right-hand side. But where did it come from? The left-hand side. So what are we going to do to show that those electrons moved? Well, I'm going to start my arrow where the electrons exist. Where did they start? The left-hand side. Where did the electrons go? There's my arrow. That arrow now shows how to move the electrons. Sorry, that looks like another head on there. on how to move from our left resonance structure to our right resonance structure.
Do we have to show lone pairs moving?
Um,
Or something of the sorts?
wait a second, I drew that totally wrong. Let's take a closer look at that. Does that work?
No,
What's wrong with it?
the dot line.
Okay. If we take a look at our electron count, our leftmost oxygen needs to have 8 electrons. It has 8 here. What happened with this arrow motion? We took 2 electrons and we moved them the other direction. Okay, which sounds reasonable. We want the double bond to be on the other side. But what happened to our oxygen? Lost electrons. So when we shift our electrons, we have to be careful that we represent what actually occurred. It's not just picking up the bond and moving it to a new place. It's figuring out where that bond actually went. Okay? So if we did this arrow, we don't get that proper structure. Everybody see that? Okay? So where did those electrons go then?
To the lone pair on the left.
If we take a look at our comparison between our structures, it's not just that we moved the double bond. Okay? Something else changed as well. If we take a look at that leftmost oxygen, how many lone pairs does it have? It has 3. If we take a look at our leftmost, 2. It had to get 2 electrons. Where could it get those 2 electrons from? So like that? What we'll do is take it from the closest source. Where's our closest source? That double bond. We will take the electrons from our double bond and now put them as a lone pair on our oxygen. Oxygen started neutral, just gained electrons. What happens to its charge now? It should become negative. And if we look at our rightmost structure, good job. It's negative. And there's our lone pair that I'm trying to highlight there in the blue. Okay? So that gets us part way. We now have that single bond, but what's the other half of our structure? What else changed? We are taking the lone pair and moving it in to make the double bond.
So the bond's not moving, it's the electrons that are moving to the bonds.
Yep. So when we discuss organic chemistry, again, what do we move? We move the electrons. We aren't moving bonds. We're moving the electrons in the bond to match up with how things should shift around. Okay? Takes a little bit of practice to work with, and things that might seem intuitive. Our very first arrow said we just pick up the bond and put it in the other spot. But it didn't work. Okay? We're not shifting the bond, we're shifting the electrons. Make sure the electrons end up in the appropriate places, and it may not be as obvious as it looks. Okay? Questions on that?
Why here's remove the bond?
In the previous example, we moved the electrons that happened to be in the bond. So when we do the discussion, even in this case, okay, we are moving a bond. The blue arrow shows a bond moving. But it's not the bond, it's the electrons in the bond. In the cyclopropenyl example that we looked at, it looks again like the bond moved. No, the electrons in that bond moved to being in a new space that happened to make a new bond. We're not moving bonds, we're moving electrons. Okay? Really, really fine line on that. Okay? Because in both of them make up or made up by electrons. Okay? If we now go back to kind of priority for best, okay, we want to make sure that if we're drawing out our Lewis structure, that we satisfy our octet rule. So if we take a look at these two structures, are our octet rules satisfied? Yes. So according to our Lewis structures, at this point, these are both equivalent. We should show them both. Okay? Rule number 2. Minimize charge. Is our charge minimized or the same in both of these structures? No. So what does that mean? These two structures have varying energies because our priority rules prove that. So what we end up showing is saying, okay, I want to minimize charge. Which of these has the smallest charge? The first one, or our left. That ends up being my valid structure. And I ignore the other one. In quotes, ignore. Okay. Why might I want to not ignore that other structure? When we look at reactivity, we're concerned about charge. What's the charge in our leftmost structure? There is no charge, so nothing is obvious. If we look at our rightmost structure, which again represents the same compound, do we see charge? Yes. We have now identified a way this molecule can potentially react. Okay? So typically our first bad Lewis structure, or our first bad resonance structure, gives us a lot of information about the reactivity of that particular compound. Okay? So you want to not ignore it, realize it's there, and then maybe as we move into reactions, you can then start to take advantage of that information and start to predict where and how things will react. If you don't have an understanding of resonance, you don't see that reactivity, so that when we get to that section, ultimately, you say, oh, I got to memorize something new. What you should have memorized was how to draw resonance structures, and then you didn't have to memorize the reaction. Okay? Questions about that? Yeah?
I have a question about the arrows. Is it the 2 points on the end is when we do 2 electrons?
Yes. So there are, in this drawing right now, we have 2 types of arrows. Okay, we have 2 curved arrows, and you'll notice both of those curved arrows have a double head. That double head means that we moved 2 electrons. Is it possible to move only 1 electron?
Yes.
It is. Okay. What would we refer to that reaction as if we're only moving 1 electron? Someone said it. Free radical reactions. We'll see radical reactions towards the end of the semester. I typically don't like them. Our bodies tend to not like them as well. Any ideas why? It's not that they're carcinogenic. They're highly unstable, and they will react with pretty much anything that they can possibly see, which means predicting radical reactions can get very dicey. Right? So if you ever wanted to make something, you're told you got to make it from another starting material, just make it a free radical. Eventually it'll get there. We may have a horrible yield, but eventually it makes it. Right? So we kind of want to be aware of those possible things. What's the other arrow that showed up in here instead of our blue and orange curved arrows?
Straight double-headed arrow.
We have a straight arrow or red arrow in between. I keep wanting to say what the term is, and I can't. Here, let's circle it. I'm just going to try and use another arrow to point to it. This arrow isn't an equilibrium arrow. Okay? It's used for a very particular reason. It is very commonly used by people not in organic chemistry to represent equilibrium. It is an awful explanation. What does equilibrium look like? One direction and the reverse direction. That is an equilibrium arrow. What does our red arrow show? Resonance. Okay, it is only used in resonance. It shows no reaction. All we're doing is moving some higher energy electrons through our structure. Okay, so be aware of that. And I'm pretty sure at the end of one of these slides or sections, I've got a summary of all the arrows that you'll see. Okay? More questions? Okay, I do kind of want to start at 15. No, that's not too bad. Okay. Ultimately, with these Lewis structures, all we're really trying to get you to get to is kind of this summary, being able to recognize patterns within it. Okay? In 151, they just have you draw out all these structures and say, hey, look, you got a pretty structure, but you don't have to recognize any patterns behind it. In organic chemistry, remember, we simplify down to ultimately 10 elements. We want to know the bonding patterns for those 10 elements, and we could really care less about anything else. And if we know how those 10 elements bond, we can make a massive shortcut. That massive shortcut gets rid of, where is it? Somewhere back there. All of our Lewis structure rules. If I know carbon needs to have 4 bonds, I don't care how many valence electrons it has. It needs to have those 4. If it doesn't have those 4, there is something else going on with it. Right? So kind of the idea behind the Lewis structure is to get you to think back to how you built those and then do enough problems that you recognize these patterns. That when we look at carbon, it comes in with 4 valence electrons and it ends up with 4 bonds. Do those bonds all have to be single bonds? No. They can be multiple bonds, but there has to be a total of 4. Okay? This will only be true when carbon is in its neutral state, so no charge. We need to go through and memorize this as well for our nitrogen, our oxygen, and ultimately our halogens. Right? So once we recognize the standard bonding patterns, we don't have to count out all the valence electrons in a structure. And if we gave you a massive structure, you'll be very thankful that you bothered to memorize these as opposed to counting out all the electrons. Okay? Is carbon always going to come out neutral? No. How about nitrogen? No. Oxygen? Chlorine? No. We're going to get varying charges potentially showing up. So not only do we have to know their neutral state, we also have to know their charge states. All right? If carbon is going to come out and be a positive charge, it needs to have 3 bonds. Why can it only have 3 bonds in the positive charge? To become positive, what does it have to do? Lose electrons. Well, if it loses electrons, we have to get rid of one set of electrons there, which means getting rid of a bond. Okay? We could go through and do the same kind of idea with our nitrogen, oxygen, and our halogens. With our nitrogen, it's a bit interesting. In our neutral state, we start with 3 bonds and a lone pair. To become positive, what has to happen? We have to lose electrons. So we could use carbon as our example. We remove a bond. There we go. We'd have a positive charge. Seems a bit odd. Is that what's shown up here? No, we actually gained a bond. If we gain a bond, don't we gain electrons with it? Where did that bond come from? The sharing of what electrons? The lone pair electrons that were on our neutral nitrogen. We took those 2 electrons that were only associated with nitrogen, and we've now spun them, so one is associated with nitrogen, and the other one is associated with the other atom that it's connected to, which means what did nitrogen do? Lost an electron to that other atom by adding a bond. Okay? So being aware of how the electrons balance and shift through a structure can get you to these different charge states. How much of that is strictly necessary to know? Arguably, you don't need to know it. You just need to know what it looks like. So that if I draw out a negative nitrogen, you know that you've got 2 bonds and 2 lone pairs. Okay? Why did I not show a -2 or a +2 structure for any of these? Is charge good or bad? Charge is bad. So if we've got a negative charge, what's that nitrogen going to immediately do? Going to react to neutralize that negative charge. What's the likelihood that we would ever get up to a -2? Not very likely. Okay, that's going to end up being ridiculously reactive, and it's not going to have a lifetime long enough for us to actually deal with or work with in the organic lab. Okay? So we're really focused around neutral, single positive, single negative. Be aware of those bonding patterns. Make sure you've gotten them nailed down so that when you start drawing your Lewis structures, you don't have to stress as much about them. Questions? Okay. Do you think the shape of any of these is going to change the interaction? Yeah. How something is physically located is definitely going to change the interaction. Right? For instance, if we had the chairs all turned around facing the other direction, would we decide to change how the building or change how the room is organized? Yeah, we'd probably put the projectors on the other wall, okay, or vice versa. Shape has a huge impact on the overall relationship, okay, or how it can interact with other molecules. Okay? Does Lewis structure give us shape? I mean, I look at those drawings. That looks like a reasonable shape to me. But is it a valid shape for the 3-dimensional world? Unfortunately not. When we put electrons into orbitals, how many electrons could we put into an orbital? 2. Why only 2?
Because they're in opposite spins.
They're opposite spins. Why do we care about the opposite spin?
It has to do with how they're going to move and react with the
Kind of, sort of.
adjacent atom.
You're making it more difficult than you have to. But you're right.
They fill, like they will fill going up, and then they fill.
What happens when I bring a negative near a negative? They repel. Okay, so why can I put 2 electrons into an orbital if they repel? They have opposite spins. Okay? So what we're looking at is a repulsion of electrons. What does any one of those lines represent? Sharing of electrons. What are those electrons going to do? Repel away from every other source of electron they possibly can. Right? Each of those lines has a pair of electrons confined within that space, and each of those lines are now going to repel away from every other line as much as it possibly can. So what we can start to do is go through some geometric mumbo-jumbo and start to evaluate how those electron groups bounce away from each other. Let's see. So if we took a look at methane, if we draw it a little bit bigger, we would assume, because all of those hydrogens are the same, that the bond angles between all of those hydrogens would be the same. What's the bond angle? Upper right-hand quadrant. That's drawn. That looks like 90. How about that one? 90. How about that one?
90.
What's wrong with this? They're all 90 degrees. They're all perfectly equally spaced from each other. Why is this not a valid structure? What's the bond angle between these 2 hydrogens? 180. Are all of these equally spaced? No. Okay. Lewis theory does not actually reflect a 3-dimensional structure. What is the proper bond angle? 109.5. We end up with the tetrahedral shape. So VSEPR, or valence shell electron pair repulsion theory, came about from taking the Lewis structures and now putting those into 3 dimensions. Okay? And if you pushed the VSEPR models beyond carbon, you can get into all sorts of fun things. Octahedral, T-shape, seesaw. What's awesome about that? All of that is beyond carbon. What's awesome about organic chemistry? We like carbon. So we don't have to worry about all those other shapes. What we're going to be concerned about is ultimately our tetrahedral shapes. Okay? So we end up with 3 main categories: our tetrahedral, our trigonal planar, and our linear shapes. Okay? Within these categories, what we're looking at is the groups of electrons around an individual atom. Okay? And in particular, we're looking at bonds in this case. So if we looked at carbon, we had 4 groups of electrons. We slide into the tetrahedral shape. Okay? This typically gets referred to as the electron geometry. Well, why? What happens if we jump to something like NH3? And because you're all lightning fast at drawing Lewis structures, you should be able to give me the Lewis structure for NH3 in less time than it took me to say that. And we'd go through around that nitrogen and again evaluate how many groups of electrons are there. 4. Okay? How do we determine the groups of electrons? Well, remember, Lewis was based off of a cube, which we simplified to a square. How many sides are on a square? 4. So what we will do is look for a group of electrons on any one of those sides. How many groups of electrons do we have? 4. 4 groups of electrons suggest the tetrahedral shape. We would expect the exact same shape as methane. Do we get the exact same shape? No. Why not?
It's just a lone pair, there's not another atom on top.
The lone pair of electrons is occupying a different space than the bonding electrons. How different is that space? What makes it different? What was that? I think I heard you say. Right. What does that do about the distance that those electrons are from the central atom?
Can be farther.
They're closer to the central atom if it's a non-bonding pair. So if we take a general shape, those of you from home can't see this, we take a hand, we use my hand as a tetrahedral shape. Okay? The center atom is right in the middle. We've got the top being my wrist, and what is that? pointer, middle, and thumb being our tetrahedral shape. Okay? If we go through and now switch this to nitrogen, we're saying that that top electron is now actually pushing down closer to the nitrogen. What happens to our bonds?
They flatten out.
Okay? So remember, our electrons are pushing down. Use the iPad for this. Hopefully not ruin anything. Maybe have been a bad idea. The electrons are pushing down from the top, my wrist. Okay? If we push down and those flatten out, where did those bonds move? Did they move closer to my wrist or further?
Farther away.
Closer to your wrist.
They move closer to my wrist. What do our, man, I'm really advancing. Where do the electrons want to go? As far away from other electrons. What happens to the bond angle when we put in a lone pair? The bond shrinks. So when we move to a tetrahedral shape, we end up with a smaller bond angle than we'd get in a trigonal pyramidal shape than we would for a tetrahedral. I'm going to get it back awake. Okay? So in that logic, what we'd end up doing is ending up with a slightly different shape. Because it is slightly different, okay, as we do with all things, we call them something else. So we end up with a new name. We end up with tetrahedral. If we ended up with, instead of just one non-bonding pair of electrons, but two, what happens? We again change the shape and we get something known as a bent shape. Really, we're getting those differences because when we look at an individual structure, okay, if I was going to look at a molecule and I had my ammonia structure up here, and I looked at that molecule in reality, what am I going to see?
Little tripod too.
I'm going to see the atoms. Okay? I'm going to see this big group of electrons representing each of those atoms. Well, where's this lone pair? It's associated with the atom. So when I look at that model, I don't see this nice tetrahedral shape of 4 separate objects. I see one of 3 separate objects. But they don't push into that trigonal planar because that nitrogen's lone pair is forcing it into that tetrahedral shape. Okay? So it's trying to represent how those electron groups change and alter our shapes. Kind of neat. Okay, so that's what our VSEPR models are doing, generating shapes from Lewis structure. Okay? You will see a lot more advanced versions of what this slide is showing. Remember in 151, you probably saw what comes after tetrahedral? Trigonal bipyramidal and your octahedrals, and then all of those split out into further groups. We don't have to worry about those. We just have to get up to that tetrahedral. Most of organic chemistry falls into which category? Tetrahedral. Because we're dealing with carbon as our center atom, okay, which is almost always going to hit that tetrahedral shape. And we'll shift it some variation off of that. Is there some exceptions to that? What was a positively charged carbon? How many electron groups are there on that? 3. We end up with that trigonal planar. Okay? So we will shift off of the tetrahedral, but tetrahedral's our primary shape. That's going to be the one we're going to focus most of our time on. We'll see some trigonal planar. We rarely venture into the linear, but sometimes we'll see that as well. Okay? As far as what you need to remember, you should be aware of the shapes. You should have an idea on the bond angles. You can tell already that I don't have the greatest idea. I meant to look that up. But you should have an idea on what's happening when you change from a bond to a lone pair. What happens to that bond angle? So when we look at our tetrahedrals, we go from tetrahedral to trigonal pyramidal, that bond angle crunches down tiny, a little bit smaller. So we go from trigonal pyramidal to bent, that bond angle gets even smaller. Okay? What happens when we get to linear? Now astronomically jumps up the other direction, and that's because there's now really only 2 groups. Okay? So kind of be aware of those. You're going to need to be able to manipulate that, and we will add some more information to it as we move in through the next topic. Okay? What we just looked at with Lewis was where electrons existed, okay, in a molecule. Have we seen where electrons exist before we even got to Lewis structures? Okay, before I make a structure with carbon and hydrogen, where were the electrons? In the valence shell, take it a little bit further, in the orbitals. So when we go through and look at changing from an atom to a molecule, we're changing the location of the electrons. Well, if orbitals existed in the atomic sense, where we had those electrons located, we'd better see a similar comparison when we move up to the molecular orbitals. We should see where those electrons exist. Okay, so what we end up meshing with is this balance between the atomic theory and the molecular theory. Okay, so let's go back to our methane structure. Okay, and I'm going to draw it slightly differently. Well, I'm going to draw it normal first. There's our Lewis structure. If we wanted to represent better the three-dimensional characteristics, we put a more appropriate bond angle in there, and then you also note that we end up showing a wedge and a dash. What do those mean?
Wedges towards, dashes away.
Away and towards. Okay, the wedge is coming towards you. Okay, it's getting bigger. Think as something gets closer and closer towards you, it gets bigger and bigger. Okay, think about the exam. Right now, you probably don't care about it, but if the exam was today, you'd probably all be panicking and freaking out. It becomes a lot more real. It's a lot bigger to you. Okay, so that's what our wedge is showing. What was our bond angle in that case? 109.5. Okay, so what we now need to do is reconcile our idea of these molecular orbitals, which is ultimately where our electrons are existing in our methane structure, and our atomic orbitals. Okay, so we're taking the electrons from our atom and we're putting them into these new bonding orbitals. Okay, well, if everything works out, what we would expect is our atomic orbitals would perfectly align into our molecular orbital shape. Okay, so what's the bond angle between the x-axis and the y-axis p orbitals? What's the angle between that? 90 degrees. Seems a little bit weird. Well, what's the z-axis angle between our y and our x?
45.
Still 90. Okay, z, x. You look at the proper, you're still looking at 90 degrees. Okay. Why is that problematic?
Not 109.5.
If we're forming a bond, the electrons in this p orbital, the electrons, in fact, all three of those p orbitals, need to match up to be 109 degrees away from each other. They are not in the atomic orbitals. So what do? Okay, what most people would panic and do is, oh crap, all the theories are wrong. Give up. Okay, no. Okay, that's not how science works. We go back and we adjust. We say, okay, something else has to be going on here. Okay, so we're going to have to play around with it. Where did we get the shapes from? It's probabilities of where the electrons exist. Remember, they're not moving on a defined path. They're just existing somewhere in that space. So these orbitals are very mobile. Okay? We can disrupt and reshape them as much as we want, much like clay. So some, perhaps, artist went through and said, well, if you're telling me it's just like clay, and I need 4 orbitals that are all supposed to be the same, okay, equal, I'm just going to take all the 4 things that you gave me to begin with, I'm going to mash them all together, and I'm going to make 4 new ones. Well, you can't do that. Actually, yeah, we can. Okay? That's hybridization theory. It's trying to cross the balance between the shape that we know to exist with molecular orbitals and the shapes that we know to exist with atomic orbitals. And all we're trying to do is reconcile those 2 shapes as best we can. And we're going to do that with our hybridization theory. Okay? To really push this to the extreme, really what we have to jump to is something known as the linear combination of atomic orbitals, molecular orbital theory. Okay? It's a fun thing to say when you string it all together. Okay? Feel free to go home and test that out. Okay? Usually involves very high-powered computers to be able to propagate and manipulate all of the data for how the electrons move and then combining how the electrons move in one atom with another atom. Okay? Turns out the complexity of those calculations is big enough that I think even methane becomes a challenge. Okay? That you're looking at days for the calculation to really completely 100% fully compute on a computer. Okay? So it's a pretty advanced thing. When we go through and manipulate it, nowadays we end up making some simplifications that shorten the calculation time down to maybe a couple hours. Okay? But that's a lot of extra effort, and you probably don't have a supercomputer. So what you want to do is use our hybridization theory to pretty much just magically make this happen. Okay? And that's ultimately what our computer is doing. It's combining all of these numbers and just adjusting it. So what we would go through and do is look at each of our shapes and say, what do we need out of that shape? Okay? Once we got what we need out of it, we'll go through back to what we have and say, what do I need to put into it? Okay? So we start with our atomic orbitals, play some magic, shuffle it all together, and spit out some new orbitals, depending on what I needed for the molecular orbital. Okay? We cannot create or destroy matter. So if I start with 4 orbitals, I had better end with 4 orbitals. It's a bit challenging if that doesn't happen. The sp3 is probably the easiest to analyze. So let's start with that one. Okay? In an sp3 situation, what we're looking at is methane. Okay? Again, I'm just drawing the Lewis structure. When we go through and look around methane, we again want to evaluate the groups of electrons around it. Okay? Those groups, again, we're going to evaluate the sides of a square. How many groups of electrons are around methane? 4. Which means I need 4 molecular orbitals. If I need to end with 4 new orbitals, what orbitals do I have to put into it? Well, how many atomic orbitals did I start with? 4. If I need 4 at the end, how many do I have to put in? All 4. So what I'm going to do is put into my magic hybridization machine all 4 of my orbitals, my atomic orbitals, and I'm going to have it spit out 4 new mixed up orbitals. Okay, and this, to me, is I think where that kind of confusion, or where some of this confusion can come from. What do we then call those new orbitals? Okay, chemists brilliantly simple in this response. Each of those 4 orbitals is known as the components that made it up, the sp3 orbital. That would be like if all of our names were the combination of our parents' names. Okay, on forever. Okay, our names would get very complicated. Okay, thankfully we only have parents of S and P in this case. Okay, why sp3? There were 3 p orbitals that I had to add into it. Okay, what happens if we change our shape? Okay, let's switch it up to, I'm going to do BH3. Again, this is something that you should be able to do with your Lewis theories. And you should end up with this shape, or that Lewis structure. Anybody notice anything weird about that Lewis structure? There's no octet on the boron. Does boron need an octet? No. Okay. So now the next question. How many groups of electrons are around that boron? 3. Okay. So I go back to my molecular orbital theory and say I need 3 orbitals, all exactly the same. So I go back to my atomic orbitals and say, okay, where do I get 3 atomic orbitals that are all the same? Do I have 3 that are all the same? Okay. I'm hearing a lot of the answer, but let's step away from the answer. Are there 3 orbitals that are all the same in the atomic orbitals? There are 3 p orbitals. Why do I not do just p3 as my hybrid orbitals? Why do we need S? It is lower in energy. Remember what I said to you? Got to keep going back to energy. Always do the lowest energy first, lowest energy first. We have to hybridize the s orbital because it is the lowest energy. If we're going to make a bond, we have to go to a lower energy state. Otherwise, it doesn't make sense to make that bond. Okay? So we have to hybridize the s orbital. So if we go through and try and decide, I need these 3 groups, and I know I have to use the s orbital. Okay? Well, I need 3 groups, which means I have to put in 3 orbitals. One of them is an s. What other orbitals can I put in? I can put in the px and the py, okay, or the px and the pz. That gets pretty tedious. And what we end up writing instead, sp, it's typically said as 2, not as squared, because we're using those 2 p orbitals. Okay? The student mentioned this to me, and I thought it was ludicrous that they did it, but it works. We have a superscript power in front of the s, or after the s as well. It's 1. There's one s orbital there. What's 1 plus 2? 3 groups, 3 bonds. Interesting. What happened with our CH3? Because that can't possibly work continuously. That just doesn't make any physical sense. We needed 4 groups of electrons. What was our hybridization? sp3. 1 plus, oh crap. Sure enough, take a look at your groups of electrons. You can add up the superscripts on your S and your P to get the number of groups of electrons that you need to generate the hybridization. Okay? Kind of a handy trick. Okay? What we're looking at is, again, how can we build these equivalent orbitals? You'll notice that as we moved up, when we started at our lowest energy, why would the SP, sorry, never mind, ignore that statement. If we take a look at our sp3, they're all just sp3 orbitals. Okay, what happens when we moved up to our sp2s? We needed 3 sp2 orbitals. But I started with 4 atomic orbitals. If I have 4 orbitals on the reactant side, I need 4 orbitals on my product side. Just because I've now converted 3 of them into this new sp2 orbital, I still have to have 4 total. What is that 4th orbital? It's a leftover p orbital. A p orbital that I did not need to hybridize. That p orbital, what's fun about an extra orbital? What can I put in an orbital? Electrons. Okay? Those p orbitals we can use for multiple bonds. When we move up to the sp hybridization, we're now just looking at 2 hybrid orbitals, 2 new hybrid orbitals. We took one s and one p. So if we go through and eliminate, we got rid of our s, we got rid of a p, what's left over? 2 p orbitals. So if we look at our molecular orbital diagram, we have 2 leftover p orbitals that can now, again, potentially accept electrons. Okay? Questions about that? I'm pretty sure the next slide does the exact examples I just crammed into this one. Okay. Which we'll look at here. Ooh, this is a good little statement to make. The number of orbitals in our hybrid equals the number of sigma bonds. Okay? So a couple statements that can come with this. If we take a look at the number of orbitals used in our hybrid, in our sp3 case, how many orbitals did we use? 4. How many bonds or groups of electrons did we have around it? 4. Think back to methane. I've also introduced this concept of sigma bond. Okay? Sigma we kind of talked about as a single bond. Okay? If we look again at our CH4, whoa, go away. Again at our CH4, what types of bonds are in CH4? Don't give me sigma. You're right, but not here yet. Single bonds. Okay? So we got single bonds. What orbitals are used to make those single bonds according to our carbon? sp3. What was the first orbital used? An s orbital. What does sigma begin with? S. Where is sigma coming from? Using s orbitals to make that molecular orbital bond. What's the other type of bond? Don't tell me double now.
Pi.
Sigma to pi. Where did pi come from? That's a bit interesting. So let's take a look at that. So we looked at the BH3 already, so let's take a look at CO2. We've drawn out CO2 a whole bunch of times. Probably should have picked something more exciting, but if we draw this out, and I want to evaluate the hybridization of that carbon in the middle. How many groups of electrons are around that carbon? 4 and 2 are very common answers. Okay? 4 is technically going to be wrong. Remember, what we need to do to find our groups of electrons is draw our box around our carbon. Do I have a group of electrons on that side? Nope, that doesn't count. Do I have a group of electrons on that side?
No.
Nope, doesn't count. Do I have a group of electrons on that side?
Yep.
Yep, there's one group. How about that side?
Yep.
Yep, there's another group. That group happens to have more than 2 electrons in it. That's irrelevant. We don't care. We didn't say how many pairs of electrons. We said how many groups of electrons. All right, so now I'm going to back up through all that. So we got 2 groups of electrons, which means what type of molecular orbital do I need? What's my hybridization need to be? 2 groups. We need to use the s orbital to hybridize, and since we need 2 groups, we have to bring in another orbital. We'll get sp. And we could go through and specify the 1 on each of those. We tend to get lazy and just say sp. Okay. We can now go through and draw those. Where should that sp orbital show up as far as energy? Okay, so these dotted lines that I've got on the right there are supposed to represent the energy of the s orbital and the energy of the p orbital. Where should the sp orbital be drawn?
In between,
Why should it be in between?
because it's hybridized between the two of them.
It's a mix of both a low energy and a high energy state. It's going to be somewhere in between those two. Okay, because I really don't want to draw them, and I'll have to draw them eventually. But we get our 2 sp hybrids in there. Okay. What's left over? We get 2 p orbitals left over. If we go through and now try and evaluate what's happening with our carbon and looking at the bonding, those sp hybrid orbitals, we can only put 2 electrons into each one. One coming out this way, to interact with our oxygen. Where's the other one? The complete opposite direction, 180 degrees the other direction. I can only fit a total of 2 electrons into that system. Okay, why is that important? How many electrons are around our carbon? 8 electrons. Our hybrid orbitals can only explain the presence of 4. What happened to the other 4 electrons?
From the oxygen.
Okay. If oxygen's even going to contribute electrons in, it needs to have a place to put them. What's in that space right now between the carbon and the oxygen?
Double bonds, pi bonds.
The sp sigma bond, right? How many electrons can we fit in that space? 2. Can oxygen bring and put more electrons into that space? No. Electron repulsion. How do we get more electrons occupying that space? We can't get them immediately between the atoms, but what we can do is take a look at one of those p orbitals. Right? We take a look at the easy p orbital to draw on the plane of this paper. That carbon has an extra p orbital sitting on it. Right? If we go through and evaluate the hybridization of the oxygen, we're going to end up with the exact, or an sp2 hybrid. There's going to be a leftover p orbital on our other oxygen too. Those p orbitals need to be able to share electrons. So what ends up happening? Okay, we get this quantum effect of electron tunneling, and the electrons on one p orbital say, hey, I see a p orbital lined up perfectly with me on the other side. Whoop, I'm going to jump over. In the process of that jumping over, what have we done? How do you make a bond? You share electrons. So that p orbital overlap between our carbon and our oxygen are generating our second bond. We're still putting electron density between the carbon and the oxygen, but not immediately in between them. It's a little bit higher than both atoms, higher and lower technically because of the p orbitals. What does that mean about reactivity? Which orbital would I expect to be, or which electrons would I expect to be more reactive? An electron found in my p orbital or in my sp orbital?
P orbital, because they're already further out.
My p orbitals, they're further away. What kind of electrons could we move in resonance?
P orbital, or P orbital.
The
Pi
pi electrons, or the electrons found in our p orbitals. They're higher in energy. We're allowed to shift them around. Okay? The sigma bond, we can't move because it's that much lower in energy. We're not allowed to shift that electron density. Okay? This is where we get the concept of a pi bond. Okay? The pi bond is different from a sigma bond. A sigma bond involves s-type orbitals. They can be hybridized, and it's a direct overlap of the orbitals. The special part about the pi bond, we're involving p orbitals. Okay? We can't get those 2 p orbitals to directly overlap with each other because then we start overlapping too much of the sigma bond in between. So the pi bond is slightly different from the sigma bond, and that we don't get direct overlap of orbitals. Okay? But what we do get is as long as those p orbitals are in the same plane, they can share electrons. What happens if I rotate it and say the p orbitals are not in the same plane anymore? We now no longer have the ability to shuttle electrons through it because the orbitals aren't in the same alignment. So we could say that the pi bond broke. Right? What does that mean for us if we took a look at some other examples here? For instance, if we drew out these structures, oh, I knew I should have just drawn this in already. And let's take a look at the middle one. And again, in theory, you guys will pick up the speed hopefully faster than me and neater than me. But if we take a look at this, okay, what's the hybridization in our first structure? What's the hybridization of our carbons? sp3 for both. What's the hybridization in the next one? Is green okay? Kind of works. We're looking at sp2 for each of those carbons. If we look at the bond between our carbons in our first one, we've got an sp3 and an sp3. That is a direct overlap of those bonds. What happens if I take one of those carbons and I spin it like a propeller? What happens to the overlap? Absolutely nothing. We maintain the electron density between the atoms with a sigma bond, okay? Which means I can freely rotate about a sigma bond. Kind of cool. Okay, well, maybe kind of cool. So we can do a rotation here that has no effect on the bonding characteristics. What happens when we move to our carbon or our next structure?
You disrupt that pi bond.
Okay. Yes, we still have that sigma bond that we can freely rotate about, but what's our other bond? It's a pi bond. That pi bond is relying on the overlap of p orbitals, okay, or the alignment of p orbitals. If I go to rotate, what happens? I break that bond. That rotation now becomes a disfavorable situation. I took two p orbitals, okay, that we're now sharing with each other. That drops their overall energy, right, because we can now share the electrons back and forth between them. If I rotate it, I now can no longer share those electrons, which means the energy of those orbitals goes up. So if we look at the double bond, would we expect to be able to rotate about that carbon-carbon bond? No, because of that p orbital alignment preventing the rotation. We would lose that balance. All right? What happens if we move up to the triple bond? If we were going to try and draw out the triple bond, let me just erase everything now. Our very last one, you should end up with this structure. What bonds go into making the triple bond? We have one sigma bond with the direct overlap using our hybridized orbital, and we'd end up with two pi bonds. If we then tried to rank these, which of these, single, double, or triple, would be the hardest one to rotate? The triple, because I'd have to break two pi bonds in the process of going through and doing this. All right? Yeah?
With the triple, like, would they be increasing over reactivity that you showed us with the,
What happens to that bond length? It's going to shorten the bond length because we're sharing electrons more and more. What we could now start to do is look at reactivity, and that's going to open up a different can of worms here. Okay? If we look at the reactivity between the pi electrons in our triple bond versus a sigma bond in our single bond, the pi electrons are higher in energy. We would expect those to react. Turns out that is something we find. Within a standard alkane, just sp3 carbons, we get very little reactivity, very difficult to initiate those. Pi bonds, on the other hand, react fairly well. What happens if we jump up to the triple bond? What would we predict for the reactivity of our triple bond in comparison back to our double? It should be higher reactivity because higher energy, we're dumping more electrons into that same space. Those electrons want that freedom to move out. Okay? It ends up being even more reactive than our double bond. We'll propagate that reactivity even further out into our hydrogens when we look at acids and bases. Okay? That hybridization effect of that carbon does affect every other atom it's connected to. So it's kind of fun. Are we done at 12:30? Sweet. Well, sweet for me. I can keep talking. Yeah, it may suck for you guys. You have to listen to me. Okay? Our shape summary, I added one extra column in here, our hybridization. So if you have 4 groups of electrons, you are sp3 hybridized. 3 groups of electrons, you are sp2. Okay? 2 groups of electrons, you are sp. Did we just look in a case of sp?
Yeah.
The triple bond was 2 groups of electrons. One group being the triple bond, and the other group being the single bond out to our hydrogen. So we can get into those other hybridizations. Okay? How quickly should you be able to identify the hybridizations?
Right away.
Okay? This is something that should be faster than the snap of your fingers. If I draw a structure and point an arrow at any atom, you should immediately be able to identify the hybridization of that atom. Okay? That fast. It must go quickly. Okay? And that's because we need to be able to propagate that information into how that atom can now react. If you don't know the hybridization, what you then have to do is memorize how it reacts. You can do it, but everybody complains about memorizing in organic chemistry. Here's how you don't have to memorize. Okay? Back to resonance. Okay? What orbitals were the electrons that we were allowed to be moved? We're looking at our p orbitals. If you look at lone pairs, which are also allowed to be moved, those are technically in sp. They're in some type of hybrid orbital. They will be allowed to be moved through resonance because we can end up converting that lone pair by adjusting kind of the bond angles within the structure to slide them into what is effectively a p orbital. Right? So when we're dealing with resonance, we're really thinking about how we can move pi electrons or p orbital electrons, okay, with lone pairs. What's the balance between those? Okay? So just remember that when you think back to drawing more resonance structures. Okay. Cool. I think we'll actually get where I kind of wanted to be. Drawing organic molecules. Okay. I'm going to suggest that you go through and try and draw this formula, C5H12. Okay, and I'll give you 30 seconds to draw. Fifteen seconds. Done. Anybody draw that structure? Only 2 of you. That is a perfectly valid answer for that Lewis structure. Why did only 2 or 3 of you draw that? What else did you draw? 5 carbons in a row. Why are formulas a crappy thing to use? There are way too many structures that are possible to come out of it. Okay? You'll notice that I did also do some simplifications here, which we'll talk about in a second. So when we're looking at organic chemistry, if I ask for you to provide an answer, do not ever give me the formula, because I'll cross it out, scribble it, you'll see tons of red ink and frowny face, I'll be very unhappy, and so will you. You might even have a hole in your paper where I scribbled too much. Okay? Give me the structure. So we want to go to the structures. Okay? If we went through and added some detail to this, okay, and I'm going to pick the answer that I'm not going to pick the answer that you guys drew. We could shift to something known as the structural formula. Okay? What is more helpful about the structural formula? This now starts to imply a little bit more characteristics about how you draw the structure. That parentheses is saying that I have a CH3, 2 of them, attached to a single carbon. And if you took a look at your straight line formula, you don't have that. So you would have to adjust your structure to match this. So the structural formulas are a little bit nicer. I personally find these very difficult to read. Any ideas where structural formulas originally came from? I have a theory. I don't know if it's true. We type. When you type, where did the words go? It's an obvious answer. I'm not trying to be tricky.
Left to right.
Straight line, typically left to right. Even if you went in a different culture, right to left, it's still a straight line. Okay? You might even see different cultures where it goes up and down, still a straight line. Okay? What happens when we try and draw a real structure? Does everything go in a straight line? No, we get things bending all over the place. Well, if I'm trying to type this up and present this to somebody else and I have to type it, I need some way that I can type it that actually makes sense. So they effectively invented the structural formula so that we can simplify our typing. I think this personally is going to fade from science literature. Why might it fade from science literature? Because our technology is better now that we can draw these structures relatively quickly and easily. We don't need to worry about how it types out. Right? So I think eventually that will disappear. Unfortunately, it hasn't disappeared yet, which means for your tests, you are responsible for being able to interpret these condensed formulas. So you're going to have to be able to draw out these structures, convert it into that overall structure. If we were going to draw it out as a Lewis structure, I hate drawing these, by the way, just for the record. We would have to go through, show our CH3s that are connected to one carbon. That one carbon has another hydrogen attached to it. Hydrogen can't bridge atoms, so we can put hydrogen in the middle of a formula and it immediately assumes that it's only bound to the carbon before it. Okay? That then means that that other carbon is bound to another carbon with 2 hydrogens, which is bound to another carbon with 3 hydrogens. Andy is why I might hate to draw it out like this. That took a lot of time and effort. Okay? When I first drew it, very fast, nice and easy, took 3 seconds. A bunch of lines, and it looks beautiful-ish. Okay? Here it looks like an awful mess. Okay? We could then go through and add more characteristics or more information into this. We could do a VSEPR structure. We could put in the wedges and the dashes to represent the three-dimensional shape. And if we did it on that last one, it would be even more messy. Okay? It just gets ridiculously difficult to deal with. Okay? Oh, I did draw it out. Man. And there's our little wedges and dashes, all representing the same overall structure. And you'll notice that the wedges and dashes appear to go in particular fashions. Those wedges and dashes are not just scattered randomly about. Where they're located is if you took a model of that structure and built it, and then looked at that model and tried to draw it, the wedges and dashes would match up exactly as they're shown here. What we're trying to do with our drawings as accurately as possible reflect the three-dimensional characteristics of the real structure. Okay? Takes a little bit of practice getting used to. I'm not going to take off points if for some reason you drew that central carbon. Whoops, come back here. You drew that central carbon like this, carbon with a wedge up and a dash down for your hydrogens. If you drew that, I wouldn't take off points. I'd probably circle it and say you want to look at that a little bit better. Okay? And that's just because of how we would look at that actual model. You wouldn't be able to orient the model in such a way that you would see that structure. Okay? It's just not easy to visualize. Okay? So what we're trying to do is, again, represent that three-dimensional structure. The very last thing that we would go through and do is that still brought in a lot more information, which was helpful, but how relevant was that information? What type of bond do we have between a carbon and a hydrogen? Nonpolar covalent bond. How reactive is that nonpolar covalent bond? Not very at all. So do I really care to show it? If it's not going to react, why freaking bother? Right? So what we end up doing is implying the carbon-hydrogen bond. And we can get away with that because of some other rules that align with it. So what we could draw out would be what I initially drew for this. Did I draw that right? I got that right. Well, I rotated some angles a little bit. But why is it okay to rotate the angles? They're all sigma bonds. I'm allowed to freely rotate that. Okay? So I could draw that out. Every point I've now simplified to being specified as a carbon. Since I know carbon from all my Lewis structure drawings needs to have 4 bonds, if I only see one bond, say to that terminal carbon out here, what am I implying?
3 hydrogens.
There are necessarily 3 hydrogens out there. If we take a look at the middle carbon, okay, it's a point defined as a carbon. How many bonds are shown to that carbon? 3 bonds, which means necessarily there is a hydrogen specified there. Okay? So we go through all of that Lewis theory to then ultimately back away from it and simplify things down into these skeletal forms. The skeletal form can simplify your life, but it also hides hydrogens. Sometimes that's good, sometimes that's incredibly bad. Okay? Radical reactions involve hydrogens. If you don't see your hydrogens, you don't know what hydrogen is going to react. Okay? Elimination reactions involve the removal of a hydrogen. If you can't see the hydrogen, you don't know where your elimination is going to occur. Okay? So you're going to want to consider these limitations when you go through and do those reactions. You will always see that I will simplify them because I don't like drawing them. Okay? So this is where we will end with kind of the overall summary. Okay? And I will probably throw that slide back up on Monday, but not talk anything about it. I'll just talk over you. All I'm going to do is kind of read through it. We're really only concerned about those simple elements. We've got roughly 10 of them to be concerned about. Everything else, we don't care. We simplify our shapes and our hybridizations. We don't deal with d orbitals. So we're dealing with just the tetrahedral and the trigonal planar shapes and their kind of variations off of it. After that, we move into our simplified drawings. Every point in a structure is defined immediately as a carbon. How do I know it's not carbon? I put something else there. So when we look at the structure of water, line, I want an oxygen there, and I want hydrogens out here. Okay? Hydrogens will be implied, but only to carbon. Why would we imply them only to carbon and not attached to oxygen or nitrogen? Has to do with the reactivity. The carbon to hydrogen is a nonpolar covalent bond. We don't care about that reacting. The oxygen-hydrogen is a very polar covalent bond. We would expect some reactivity there. So you can't imply hydrogens there. Last thing, this one's the most obnoxious. You'll see this in the textbook, and I will try my best to never make the mistake again as I just did with water. Oxygen, nitrogen, and your halogens almost always have lone pair electrons implied on the structure to match their general bonding format. Okay? What do I mean? Take a look at oxygen. How many electrons are around that oxygen in my water structure? Only 4 are shown. How many electrons are actually there? There are 8. That lone pair, or those 2 lone pairs are implied. Why is that a bad thing to imply? What do we move in organic chemistry? Electrons. If we take a look at the reactivity of water, which electron is going to be the most reactive? The ones in the bond between the hydrogen and the oxygen, or the ones that aren't in a bond? The ones that aren't in the bond. Okay? So be aware of those simplifications. You can start using them whenever you want at this point. Just watch out for that. Okay? Thank you for your patience and letting me talk to you more.